So anyway, all right, let me just remind you what the heck we were doing. I did post the video. I just did it, so obviously you didn't catch up, nor would you. That's how I like to accuse people of stuff. So recall that bosons, fermions, you really should know the difference, physical or analytical or inorganic. Fermions are electrons, only one per state. Spin up, spin down means 2 electrons in every orbital. And everything else is a boson. And bosons can have any number of, can populate, multitudes of states. Bosons that you might care about include photons are bosonic because they spin 1, and phonons, right? And phonons are solid. A lot of you are solid state people. Trinary works on surfaces. My nanoparticles are basically solid state materials. Cabana's people, solid state. So we have a real solid state, slant to this department. And so phonons, of course, are the vibrations of a solid. So we should cover phonons. And phonons are what give solids heat capacity, and that's what we're covering today. And the phonons are bosonic, so arbitrary number of phonons per state. And now recall that we started out with, I'm going to use a single frequency representation, and I'll fix that in a little bit. But for any kind of vibration, we've got, that's right, sorry. Think of an atom I and all the other atoms J, and so this would be, a solid material is going to be like 10 to the 20 number of atoms. That's very large. And so I am saying that there's an energetic consequence to displacing yourself from equilibrium, and that's the guy we're talking about. And then it has neighbors, and so I'm talking about running up against your neighbors right now. And notice that when I equals J, I've got 1/2 kx squared, which is Hooke's law, which you've always thought of as harmonic vibration. And again, when I is not equal to J, that's when it's hitting against its nearest neighbor. And the coupling matrix is going to be very complex. And it's going to be n by n. It's going to have a diagonal, and it's going to be full of numbers. For an atom with itself, that's going to be its spring constant. For an atom against its neighbor, that's some interaction constant. For an atom, if I is like the center atom and J is an atom at the corner, then the coupling matrix is 0 because they don't touch each other. Okay, now remember that we said that you re-represent this into phononic states, and when you do that, you get a diagonal matrix with numbers and zeros everywhere else, and that makes all of this unbelievably easy. And these are, of course, instead of rows and columns representing, up here, these rows and columns represented the position of atom 1, atom 2, atom 3. You could label atoms in a solid because they're stuck where they're at. Instead, you would have phonon modes. And anyway, in which case the energy, the problem is that in this case, this is what you have. And this is a nightmare. I mean, this is horrible. When you change the representation, you get something that's much easier to work with, especially when you need to calculate partition functions. And I'm lost in my own notes. Now here I am. And alpha, where alpha is a mode. Okay. Right, now seriously, you're going from this, which, oh my God, to that, which really doesn't look that bad. All you lose is kind of an intuitive idea of the coupling matrix of atoms, 1/2 kx squared for the diagonal terms, and then the energetic consequences of an atom bumping into its neighbor. I can kind of visualize that. This is harder to visualize, but whatever. Well, actually, I'm going to show you some examples, but the energy equation sure is easy. The analysis, the diagonalization is how you figure out what the frequencies are. So that requires a little bit more analysis, and I'm not going to talk about that today. But anyway, okay, now, so I'm still talking about phonons. Let's do what Einstein did. And Einstein's approach, I'm going to need to use the whole board most of the time. No, I have to use, I freaking hate this room. Okay, Einstein's approach. So Einstein was, around 1900. That's when they were figuring out all of this equipartition stuff. Einstein did most of his stuff before quantum mechanics, by the way, but they were also getting their thermo straight at this point, and so Einstein weighed in on some of that. Now, here's what he did. Einstein said the solid can be characterized by a single frequency. And now recall that in a solid, so he wasn't thinking in terms of phonons. He was thinking that any particular atom is vibrating in its cage, and everyone does that at a single frequency. Something a younger person would say, but not correct. And let's just roll with that now. And I'll show how Debye thought of phonons. So let's free all that stuff I just said about phonons, just drop it. Einstein said every little atom rattles in its own cage at a single frequency. And he also said that the atoms are distinguishable. And the reason that matters is that if we're going to solve this in the canonical, that you take the partition function, the energy of a phonon, and I just wrote it down a minute ago, raise it to the number of atoms. If the atoms are indistinguishable like in a gas, you would divide it by n factorial. If they're not, because if I had like a scanning electron microscope, I can visualize the atoms. I can label, I can give them names like Mary and Jane, right? And so they're distinguishable, in which case this thing goes away. The thing that always bothers me is that seems very arbitrary. I mean, n factorial when n is like 10 to the 20 is unbelievably large. And while I understand that a gas phase molecules, they're buzzing around like crazy, I can't label them, and in the solid I can. What about a glass, right? What about something in between? Right, this gets real nebulous, and that really bothers me because n factorial is like a big thing to have or not to have there. Okay, that sucks, but then I realized partition functions, who cares? We don't really do that much with partition functions by themselves. We're always taking derivatives of partition functions, in which case constants don't really matter. So anyway, I'm just pointing that out. All right, so Einstein wants to weigh in on what's the heat capacity of solids. This is 1900. He makes this approximation and it ends up being lethal. He gets a lot right, but it's ultimately wrong because of that. But let's do it anyway, because we want you to be math cognizant. Okay, so I can write a little bit on this board before we go nuts. Also, well, here, let me write down. I'm going to have to do this in 3 dimensions. Notice that I'm writing a singular frequency, and that's an approximation no matter what dimension. So I'm obviously writing x, y, and z because we live in 3 dimensions. But each one is multiplied by the same frequency. This is where this will ultimately go off the rails. And now also, I keep ballyhooing about fermions and bosons. Where this is a boson is that these, hopefully you remember in your undergrad quantum, when you learned about vibrational wave functions, you should have learned that the energy of a vibration was 1/2. It was the quantum number plus a half h frequency, right? Do you remember that? Right, and the 1/2 is the 0. The quantum number was this guy. Now, what this guy is, it's obviously clearly the same equation, except this is not. It's not quite the same equation. This is now a population number, so it can be 0, 1, 2, 3, 4, 5. So it can be. If it could only be 0 or 1, the phonons are fermionic. They are not. They are bosonic. So this can be 1, 0, 1, 2, 3, 4, 5, 6, 7, and that's why they're different. That's the difference between a boson and a fermion. All right, anyway, and the reason that matters is that when I write down the partition function, this is why I needed more boardroom. And now again, we're going to say that's a little partition function, relatively easy to take e to the minus beta energy and then let those occupation numbers go from 0 to infinity. Also remember that the boson part means that you can have 0, 1, 2, 3 number of vibrations in any dimension. Also, what else do I want to say? Oh, and they're also not interacting with each other. What that means is that if I have a lot of vibration in the x direction, I may or may not have vibration in the y direction. If there's some weird reason why they can speak to each other, they can't. That doesn't make sense. And that's another reason why I can write the big partition function as a bunch of little partition functions. Where am I at? Okay, so now this is horrific, by the way, and I don't even know if I have enough room. Now again, here is the Fermi boson part, because the occupation numbers can go to infinity. Here's the fact that we live in 3 dimensions part. I'm writing this as x, y, and z. Okay, and remember that partition functions are just e to the minus beta energy, and I have to write this down again. Sorry, I got it. Beta gets multiplied by everything, so nx plus 1/2. Then I'm going to do y. So that's one of the more painful things about this class, is just writing things over and over and over again, because it's like x, y, and z is the same thing. And in bracket, okay, there we go. And then the whole damn thing to the nth power, where n is the number of atoms. And again, if you have like a 1 gram, imagine if you're actually measuring the heat capacity of cad selenide, I don't know, cad selenide, you would have like about a gram, that would be about 1/10 a mole, and maybe 100th a mole, and so that'd have like 10 to the 21 atoms, so that's a big number. Okay, now recall that the reason that the canonical tends to be our friend is that e's and natural logs have lots of shortcuts, especially in the form of a series. So one of the shortcuts here is that because x, y, and z are basically identical, I can just say that there's one sum. So I'm just going to call that a generic n, e to the minus beta, and n plus 1/2. And then the fact that there's 3 dimensions and n particles goes there. Now again, there's no crazy math trick, it's just an identity of exponentials. It's e to the a plus b is e to the a times e to the b. That's actually where I'm getting this. So you can see why a, b, c, when a, b, and c are all equal, it's just the same, just one of them to the 3rd power. Anyway, that's where that comes from. Okay. All right, now I'm going to solve this thing. Let's forget about the 3n. So on the cume, I will probably have you solve the partition function for a very simple system, like a 2-level system. And that sounds like a fermionic system. A bosonic system, let's see, when there's no phonon mode, when it's very cold, then the ground state would have n equals 0, but instead of e to the 0, I've got a little bit of a, that's the 0 point energy, by the way. Okay, then I get, let's do the next energy level. I'm going to just factor out the 0 point energy and multiply that by the first quanta of allowed energy, and then again I'm going to factor out the 0 point energy, multiply that by the second quanta, and on and on and on. Now you might have forgotten, but all right, for one, I can factor out the 0 point energy contribution to the partition function, leaving 1 plus e to the minus beta plus e to the minus 2 beta plus e to the minus 3 beta. If you recall, there was a limiting form for this. There was a series representation. We've actually done it a couple of times now, but there it is. So again, 1 plus e to the x, 1 plus e to the minus x plus e to the minus 2x plus e to the minus 3x plus e to the minus 4x is 1 over e to the minus x. So there you go. All right, then what we do is we multiply this by, obviously we multiply it by 1, and we get a very simple thing. E to the beta h bar w over 2 minus e to the minus beta. Okay. Now don't forget that you have to raise that to the third power. So I'm writing the same thing again. Beta. Anyway, this is a kind of a famous equation in the P-Chem community. If you can follow along this far, you are considered like generally knowledgeable, which is again why I bothered to do this when I'm actually on teaching relief, by the way. I didn't know if you knew that. So anyway, there you go. Einstein's canonical partition function for solid vibration. What's nice is hideous, really not bad. And that's nice. Now, one thing, though, I always want to emphasize is if you ever do run into an equation that truly is awful, and you imagine that you very well might, don't worry about it. Often equations are 10 miles long because they contain nothing but constants. And unless you have a major problem multiplying pi times h bar, if you can muster that, then even if this was 10 miles long, you find it really wasn't so bad after all. Okay, now remember I was also saying a little while ago that partition functions by themselves actually don't do much. We manipulate them into the things we care about, and we often find that we need derivatives of these things. The derivative could be the internal energy. Well, sorry, if I take the natural log, but yeah, let me remind you that. Let me take the natural log of the partition function minus the natural log is the Helmholtz energy. That's great, but Helmholtz energy is not related to heat capacity. Heat capacity is related to internal energy. Internal energy minus Ts is the Helmholtz energy. Anyway, let me write down the partition. Let me write down minus ln q. And that ends up being 3n. Remember, natural log of e to the a is hold on, I'm confused. Anyway, that's a simple identity. I'm just blanking out right now. It's kind of easy to remember. Minus. Not that you would memorize that. Obviously, on the QM, I would give you these formulas and expect you to be able to do very simple manipulations. Okay, now again, now I've got energy, which is great. Energy is measurable. It's just not this energy. This energy is, it bothered me that the equal sign wasn't perfect. Anyway, energy is measurable, just not this particular form of energy, because this is Helmholtz energy, and Helmholtz energy is actually beta average U minus Ts. Don't forget your Legendre transforms. I will definitely put those on the Hume. That's the very beginning of this class. We covered Legendre transforms. All right, now remember that heat capacity is related to internal energy, not Helmholtz energy. So I've got a little bit of a problem. I mean, look, that's not bad. It's energy, but it's just not quite there yet. Okay, so part of the whole point of this is that at the time 1900, they knew why the heat capacity of a solid was about 3R. And I'm actually going to show you why that is. It's the low temperature heat capacity that behaves funky. That's what they don't understand. Now, if I go to low temperature, a couple of things happen. For one, T goes to 0. Okay, that's brainless. Entropy by the Nernst theorem. Remember that entropy is ultimately measurable because of the third law of thermodynamics, the Nernst theorem that says the entropy of a perfect crystal at 0 degrees K is 0 joules per K. Okay, so you may notice that this is going to 0. Beta, of course, goes to infinity. And that means that beta A is basically equal to beta internal energy. Right, you see, you don't have any, the difference between A and U is the entropy. And a perfect crystal at low temperature has no entropy. So there you go, they end up being the same. They'll diverge as soon as you start warming it up. Whatever, but we're doing this measurement at a low temperature. Okay, now let's do the limit of what we just derived of beta going to infinity of 3n ln e to the beta h bar w over 2 minus e to the minus beta. And this is why you can actually represent this mathematically a few ways. That ends up being 0. E to the minus infinity, in case you get confused at the CUME next January. Oh, is there a limit here? Just plug in numbers. Plug in e to the minus 10 into your calculator. You plug in e to the minus 100 in your calculator, it goes to 0. Okay, so there you go. All right, so that means that beta U, beta average internal energy. Remember, I have to put internal energy as an average because in the canonical, temperature is defined, but internal energy is not. In the microcanonical, the opposite is true. You learned that, but maybe you forgot. But anyway, okay, so 3n natural log of e to the beta frequency over 2, and this, of course, natural log of the e. This ends up being 3/2. Okay, there you go. Yeah, there you go. All right, so that is your internal energy. And now what do I want to do? Okay, so, wait a minute. I feel like I got a little confused here. Oh, yeah, okay. So this is your internal energy at very, 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 very low temperatures.
What happens to beta? Is there beta on the other side?
Yeah, so beta A is the minus the natural log. Beta A is beta U, approximately. And then the beta in the exponent gets pulled out by the natural log. So there's no, yeah. And there shouldn't be, but one way I would know that, even if I didn't follow the algebra, is that I have a limit. And so when I have a limit of something, that thing actually ought to disappear because that's the whole point of a limit. So wherever I had a beta, I should be putting in infinity, therefore I should have no betas. All right, so yeah, I'm not surprised there's no betas. Okay, so this guy gives me the internal energy at low temperature, but to get to the heat capacity, you may have remembered this as we go to higher temperatures. Where am I at? Okay, to get to higher temperatures, we're going to have to use a different formula for internal energy. So again, this is the internal energy at 0 K, but as we warm it up, we need to warm it up to calculate the heat capacity, because that's what heat capacity basically is. It tells us how things warm up, temperature as you add energy. And if you recall, the average internal energy is minus the derivative. Derivative minus Ln with respect to beta. Okay, so again, I've got a great formula for Helmholtz energy, but I really need internal energy because that's my heat capacity. This tells me the internal energy at 0 K, but that doesn't give me heat capacity. I need to see temperature in here because I have to take the derivative with respect to temperature to get heat capacity. It's not in here, but why would it be? I took the limit of T to 0. So now I have to inject some finite temperature, and that means I basically can't use that approximation I just used. Okay, so let's do that. Okay, minus the derivative of LNQ with respect to beta, the derivative with respect to beta of 3n ln, and I've already written this a zillion times, I'm not doing any, it's just sucky to cram all this in here. There we go. Okay, again, you've already seen me write this a couple of times, now I just have to do the derivative. And let's see, what is that? So this is the average internal energy, 3n. Okay, when I'm doing the derivative of the natural log, the thing is on the bottom. The function just, derivative of a function, the derivative of the natural log of a function is 1 over the function times its derivative. So here's 1 over the function. And then we take the derivative of the top side, which will bring down the argument of hw over 2. I'm basically doing a step ahead. And then on top, you basically get the same thing, but there's a plus now. What happened is that there's a plus because that minus got brought down and it canceled out that minus, for those of you who are following along in my ultra-fast calculus derivation. Okay, there you go. Now this ends up being, when I see these kinds of things, I know to start looking up hypertangent, hypertrig, and this ends up being a Koth. It's a Koth function of the argument of the exponential. There you go. Okay, so again, not bad. We're almost there, you know. Remember grad school, you got to be able to follow horrific derivations. As you let t go to infinity, beta goes to 0. So we're taking the high temperature limit. And it's literally before this class, I was just Googling limits of Koth. And it turns out that, where am I at? The limit of x goes to 0, seriously I had to look this up, of a Koth function of x ends up being 1 over x. Okay, so we're almost done. And we're going to be able to graph internal energy versus temperature, and of course the derivative of that thing is the heat capacity. And we're going to see that Einstein got part of it right, part of it wrong. And I'll see how far I get. Someone keep track of temperature because my watch has been dysfunctional. We might get finished. Let's see if I don't talk about my cats too much. What time is it? Is it 36? Okay, so my watch has been dodgy. Okay, so this ends up being, let's see, 3n. This is just an exercise in 2 over beta. Wait, is that right? Oh yeah. Oh yeah, 3m over beta. There you go. Okay, so that means that if I plot the internal energy over n as a function of temperature, what you get is, let's see, 3/2. You get 3/2 times the frequency, and then it actually just increases as a line, which is basically 3 kBT. Remember beta. You remember that beta is. When you go to PChem talks, you see beta. Beta is always 1 over kBT. Okay, now the derivative of that. The derivative with respect to temperature is the heat capacity, and let's do that. It starts out 0 because the slope is 0, and then when the slope increases, but then it stops changing again. So what you're going to have is the slope. Again, the slope of the straight line is 0. Then the slope turns up to it increases to some asymptotic value. So there you go. The asymptotic value at high temperature is just 3 nkV. I didn't plot that per m, so anyway, so there you go. And of course, N times kV, if N is a mole, is 3R. So there you go. Take a piece of cad selenite, a gram, which is about 1/10 a mole, measure the heat capacity, roughly a room temperature, and you're going to get 3R. Not too hard, right? Okay, Einstein got this right. Now I'll explain why the heat capacity of a solid is 3R. Here, it's not quite right. If we take this guy, essentially, I mean, you can kind of tell. You've got a lot of exponentials in here. So this part, heat capacity scales as e to the minus t. That's, I'm sorry, e to the minus 1 over t beta, right? That's bad. It should not do that. When you plot actual data, oh man, was it close. At high temperature, it's right, but I swear to God, this is not me just not drawing it right. This is really what the data look like. It's almost a perfect match, but it is not a perfect match. And even though people went gaga at first over this, they kept looking at this and saying, no, our measurements aren't off. Your equation doesn't work. I mean, it's awfully close. Gets so much right, but off is off. Like I say, if I did this, I would just say, oh, well, my calorimeter has some error. And they made better calorimeters, and it never got better. And they knew that this wasn't correct. I tell you what, let me do the asymptotic. Why is the high temperature heat capacity 3R? Because that's actually a lot more subtle than you might realize. Now, so we're going to do that, and then I guess next time we'll talk about Debye, and then we can maybe tell you what, then we'll do stock evaluation, because that's actually kind of awesome. So, what did I talk? Oh, anyway, so the problem is that Einstein uses a single frequency, and that's wrong. You can think of atoms, let's take a perfect crystal. You know that the low frequency modes are going to be like planes moving across from each other. You know, like plate tectonics, imagine like an earthquake. That's basically what's going on at low frequency. At high frequency, Einstein has it right. The individual atoms are shaking. The point is that Einstein didn't see it that way. There are different frequencies, and he only has one, and that's why this gets screwed up. You have to allow for there to be low frequencies, and you have to allow there to be high frequencies. He didn't, and so he got it wrong. Anyway, so maybe we'll do that next time. Debye gets it right. And Debye's treatment of different frequencies and how he calculated what those frequencies were is what allowed people to figure out quantum mechanics. All right, so we'll do that next time. But let me do the high temperature limit, because this is something that even with undergrad, as an undergrad, you should be able to know this. Okay, so remember the equipartition theorem? And I'm misspelling it. Which is that the internal, and I'll write that same language, the average internal energy of something, 1/2, we'll do it per mole, 1/2 RT degrees of freedom. Okay, degrees of freedom. Now this is what this is PChem 1 for undergrads, right? What's an argon atom? What's its degrees of freedom? 3. Why?
Transmission.
All right, it can bounce off the walls, that's it. And we live in 3 dimensions. It has 3 degrees of freedom. And the equipartition theorem says that its ability to move in X, Y, and Z each takes 1/2 RT of energy. It will absorb that. Okay, so degrees of freedom are 3, and therefore the average internal energy is 3 halves RT. The heat capacity, which is the derivative of U with respect to T, is 3 halves R, which is about 12.5. Go measure the heat capacity of argon, it's 12.5. It's like dead on to like 2 or 3 significant figures, and it's not out to like 10 or 11 significant figures for some other, because argon's not a perfect gas. So anyway, that's a bit of a detail, let's not worry about that. Okay. Not hard, right? Again, an undergrad can follow this. A solid, the heat capacity is 3R. How many degrees of freedom is that?
6.
6 degrees of freedom. What are they? Okay, we got 3 translations. Actually incorrect, but anyway, 3 translations.
Only 3 values.
3 translations and 3 vibrations. But
Only 3 values.
that's, okay, then that would be, then that's 3 halves R. You got the wrong heat capacity. No, there's 6, no, hold on. This has to be 6 for this to be 3, okay? That's simple, that's division for you.
Each vibration is counted as 2.
You're getting closer. Right? You see, this is actually hideously subtle. Degrees of freedom for a gas, that's easy. I have no problem imagining a gas bouncing off the walls, and I know I live in 3 dimensions. A child understands that. But when it comes to a solid, I know that each atom can rattle in its cage, but it's not truly free. I mean, that's right. They're not free. They're bound to their neighbors. So even if you say, well, it's close enough, where's your other? Okay, great. Where's your other 3 degrees of freedom? Because it's not rotating. Normally, gases have higher heat capacity because if it's O2, you pick up 2 degrees of freedom. You have 3 translations and 2 rotations. Right? But I don't think solids rotate. I mean, yeah, if I pick it up and throw it, okay, but that's not what's happening. Okay, solids don't rotate in a calorimeter. Methane has 3R. Methane has 3R heat capacity. That's because it can rotate in 3 ways because of its topology. Again, solids are not rotating, so what the heck, where did the other degrees of freedom come from? Okay, look, you don't, there's no way you know this, all right, unless you've had this class. Let me show you where it comes from. This is kind of neat. You don't run into this often. Those of you at quantum, all of you in quantum, you've actually covered this. You actually have to have been looking at the slides. Maybe you didn't realize it. Anyway, yeah, I gotta stop talking now. Okay, what it is, okay, the degrees of freedom of a solid are, you have space and potential. You have a spatial degree of freedom that changes energy. And that's basically, if I pull a spring, it has more energy. And you know that. That's Hooke's law, 1/2 kx squared. That potential energy depends on the position of the atoms. But the atoms can also, space is potential energy. Right? But you also get kinetic. You also have kinetic energy because it is moving. So there's your translation, right? It's nuanced. Okay, now let me actually make this a little bit more clear. Okay, let's look at so the atoms do vibrate. It's just that the total energy is composed of 2 components. There's potential energy and kinetic energy, right? Now the potential energy part is 1/2 kx squared, and again I'll write that as it's displaced. So now you know that that's a harmonic potential, and kinetic energy is 1/2 the speed that the damn thing is moving squared. And what you end up with, I think it's called the Virial Theorem. And
Just go through it.
And so you do recognize this.
Yes.
There you go. Anyway, so it turns out that when you have something that's contributing to energy as a square, there's this theorem that tells you how that contributes to the total energy. Yeah, I never can keep it straight. But what ends up happening is each one counts as a degree of freedom, and then of course I have 3 dimensions, so you get 3 potential energies, and you got 3 kinetic energy degrees of freedom. That gives you 6. 6 1/2 R is 3R. 3R of heat capacity. That's where that comes from. Again, I always thought it was kind of fascinating because it's incredibly easy to get this right for a gas, but all of a sudden in a solid, I mean, I like the fact that it's 3R. I'm like, oh, well, I just have to know what the degrees of freedom are. And it ends up being like shockingly subtly. I don't think anyone would ever just figure this out on their own. Well, I guess Debye did, or Einstein did, but they were Debye and Einstein. So anyway, okay, next time what we're going to do, and this is kind of important, is I'm going to show you how to do all this, but using a range of frequencies, and that's the density of states. Understanding density of states is one of the most hideously crucial things that you could ever learn in PChem, because everything has a density of states. And basically what you end up doing, okay, I've deleted it, you basically take the partition function and you just integrate it. And the integrals, remember, integrals are just sums. It's basically taking the partition function and adding in all the possible frequencies. The problem is that you have as many frequencies as basically as you have atoms. And so that sum gets intractable. But sums can be turned into integrals. Integrals can be solved. And that's what density of states is. That's how you solve density of states. Anyway, maybe it'll make more sense when we cover it next time. So we'll do that that's literally only about 5 minutes. I just wrote it a few hours ago.